everyone, my name is Shreya Dhara and this is my lab 2 on charge tapes. So the purpose of this lab is to find the charge separation between two U-tapes, and that's what we did in lab 1. So we're going to continue off of what we did in lab 1 experimentally to create a computational model that can estimate the amount of charge needed for the two tapes to float above each other, this time assuming that the charges on the tapes are line charges rather than a single point charge concentrated at the center of the tape. So here are the models we're going to use to help explain the physics part. So last time we used the electric force and electric field models for point charges. So in this first formula here, it says the electric force is equal to Q, which is a charge, times the net electric field. We can calculate the net electric field of a point charge by multiplying K, or Coulomb's constant, times Q, divided by R squared times R hat, where Q is the charge, R is the magnitude of this distance. And our R vector is the our observation point minus wherever the point charge is located. And that's what we used in lab 1. And then for lab 2, we're going to add to this, and we're going to use this formula to find the electric field of a line charge. So that's KQ over x times the square root of x squared plus L over 2 squared, where Q is the charge, x is the separation distance, and L is the length of the line. So here's a preview of my results. So from my glow script model, the magnitude of the electric force was 0.018, magnitude of the gravitational force was 0.056, and then I have some math here, which I'll explain later in this video, but I calculated the Q to be 1.205 times 10 to the negative 7th coulombs using our electric field of a line charge formula from earlier. So for our initial conditions, the system is the tape B, surroundings is gravity in tape A, and then the conditions and constants remain the same from last time. So the key ones here are the distance of from the two tapes, which is 0.035, the length of the tape, which is 0.175, the tape mass, which should actually be a little bit smaller, it should be 0.0057, so excuse this value here, and then the tape width. So here are the experimental details. So these are the same details from lab 1, so I just kind of copied it over and then I included a picture of what I did last time. But essentially, to summarize this, we measured an 8-inch piece of tape, created a handle and stuck it down on the table, and then we created another piece of tape called the U-tape, placed it on top of the first piece of tape, ripped it off of the lower tape to create this charge tape. And then we repeated this again to make two different tapes, and then we held one U-tape above the other so that they would float and essentially repel each other, and we measured this distance between the floating tapes. So that's kind of what this shows in the model here. And then in this lab, we took it a step further, and we used GlowScript to create a computational model. So that's down here. So here's GlowScript part 1. So this part of the GlowScript had the mass of our tape, so that's 0.00571. That was a correction I made from earlier. It has the net charge, which is Q, the tape length, tape distance, so those are all of our initial conditions. And then here is a function where we defined the electric field using the same electric field formula from lab 0. And then part 2 is where we create this line charge, and this code was already given to us, but this is where we create the line of charge as opposed to a single point charge. And here is the image from my glow script. The magnitude of the electric force again was 0.018, and the magnitude of the gravitational force was 0.056. And then for the discussion, it asks, what if you had modeled each of your tapes as a single point charge, like in the previous lab? So if you had done that, you would have gotten a different value. And the reason why is because we end up using different formulas. So in the first equation, it's just the equation of a point charge to find Fe, and we do the same thing where we set Fe equal to Fg, which is the magnitude of gravitational force, but you end up with a different value because you're using two different models. And then in the second one, we would use this equation over here where Fe is the electric force, and then we solve for Q. And how did I find Fe? Well, I set it equal to the gravitational force because that's what we did earlier on, and then you end up with the charge being 1.205 times 10 to the negative 7 coulombs. Why do these estimates differ? Which value is more likely to be closer to the real value, and why? Well, these estimates differ because, again, we're using two different models to represent the charge distribution along the line of tape. And I said the line charge is more likely because it's unlikely that in real life the charges would all concentrate at the center. Instead, it's more likely that they're evenly distributed along the line as more of a rod shape. So for results and sources of error, we ignored air resistance on a moving object here, so we did not consider air resistance in our calculations. And then we also assumed that each U-tape had the same amount of charge evenly distributed along the length of the tape. So those are the two key assumptions here. And then for sources of error, same as last time, because tapes may have touched other objects in transit, picking up unwanted charges, there may have been air resistance. So yeah, that's it.